What seemed impossible just a few years ago is now becoming an industry standard. A high-performance, durable, lightweight, and incredibly affordable electric motor. And the most curious thing? It wasn't created by a traditional automaker or a billion-dollar European consortium, but by Tesla itself. The same company that had already surprised the world with the Model S Plaid has now taken this technological foundation and refined it to fit into a low-cost compact car, the Model 2. The secret lies in an element that seems straight out of rocket science: the carbon graphene casing. That's right, a motor encased in ultralight materials that withstand extreme pressures and promise supercar performance for less than the cost of an industrial refrigerator motor. At the heart of this revolution is the abandonment of conventional metal components, which for decades dominated motor construction. Instead, Tesla opted for a rotor encased in hybrid carbon fiber with graphene, a material that combines incredible strength, lightness, and high heat tolerance. Inspired by techniques used in the construction of rockets and supersonic aircraft, this approach made the engine more resistant to thermal fatigue and centrifugal stresses, problems that silently corrode conventional engines over time. This change wasn't just aesthetic or structural, it opened the door to new possibilities in terms of rotational speed, torque, and durability. And we're not talking about a modest increase in performance. The data points to an improvement of up to 40% compared to the Model S Plaid engine, which was already a benchmark in the industry. This new Model 2 engine promises to deliver more power, with lower fuel consumption, less heat, less weight, and, most surprisingly of all, for less than $1,000, yes, an advanced, superior performance engine that can be mass-produced for a fraction of the price of conventional electric motors. In practical terms, this means a popular car can be fitted with the heart of a sports car, without prohibitively increasing the final cost. Furthermore, this innovation didn't come alone. It brings with it a paradigm shift in the design and economics of electric motors. The carbon and graphene-wrapped motor is not only cheaper to manufacture, but it's also simpler in its structure, which drastically reduces points of failure. By eliminating the use of dozens of moving parts that typically undergo constant wear, Tesla has created a system virtually immune to time and heavy use. This completely changes the consumer's relationship with automotive maintenance, something that, for decades, was synonymous with high costs and frequent repair shop visits. Another direct consequence of this innovative construction is durability. The Model 2's new motor is estimated to have a lifespan up to 3 times longer than that of a combustion engine. This puts enormous pressure on the entire traditional vehicle chain, which still relies on parts that vibrate, heat up, and wear out in continuous cycles. With the promise of operating for hundreds of thousands of miles without needing replacement, Tesla's motor reaches a new level of reliability. This makes the idea of a car for life much closer to reality, and even more accessible. And lightness isn't just a bonus. It's a fundamental part of the equation. The hybrid engine weighs significantly less than traditional electric motors, which directly impacts the vehicle's overall efficiency. Less weight means less acceleration resistance, less tire wear, and, of course, greater range with the same battery charge. This combination of lightness, strength, and simplicity creates a domino effect that benefits not only performance, but also comfort and economy in everyday life. This engine also represents a symbolic breakthrough. It shows that affordable electric cars no longer need to mean sacrificing performance. On the contrary, the Model 2 breaks this logic and demonstrates that it's possible to combine low cost with cutting-edge quality, as long as the engineering is bold enough to abandon the industry's traditional habits. With aggressively reduced production costs, this engine promises to redefine what the average consumer expects from an electric car. And most impressively, without resorting to exotic, scarce, or difficult-to-obtain materials. All of this reinforces a new narrative being written in the automotive industry. If motors were once one of the biggest constraints on cost and performance in electric vehicles, they are now becoming one of the biggest levers for democratizing access to cutting-edge technology. Tesla, by paving the way with this innovation in the Model 2, is signaling that the future of electric vehicles won't just be about sustainability. It will also be about performance, durability, and, surprisingly, affordability. And this combination, until recently, seemed like the stuff of science fiction. Most electric motors today face a nearly invisible limitation that prevents bolder advancements: rotational speed. They simply can't spin faster than 16. 0 RPM without suffering accelerated wear, overheating, or structural failure. And this isn't due to a lack of electrical power, but rather a physical limitation in the materials used in the rotor. When metal heats up, it expands and deforms, and when it spins too fast, it can literally rupture. Tesla recognized this bottleneck and decided to do something no other automaker dared: replace the metallic core with a hybrid carbon structure with graphene. And the result was a leap forward 25. 0 RPM, no explosions, no wear and tear, no drama. This advancement has a technical name: nano-injection tack, a technique in which a layer of graphene, just 0.1 nanometers thick, is injected between carbon fibers. The combination creates a material that is stronger than steel, lighter than aluminum, and with superior thermal resistance to any other compound ever used in automotive engines. This not only prevents the rotor from exploding at high RPM, but also dramatically reduces friction and heat generated within the engine. Tensile strength has increased from 7,000 to an impressive 10,000 megapascals, which basically means that this engine can handle the kind of force that would snap a common steel beam like a toothpick. And it doesn't stop there. Improvements in materials have made the engine 30% lighter than the one used in the Model S Plaid. Instead of the traditional 45 kilos, the new motor weighs only 38 kg. This is a complete game changer. In a car, every kilogram counts. Less weight means less force needed to turn the rotor, and this translates directly into lower energy consumption. In tests, the Model 2 with this motor managed to maintain cruising speed at 110 kilometers with only 11 kilometers of power, compared to the 15 kilometers previously required. It may not seem like much, but it represents a 10 to 12% saving in consumption just with the engine. Now, when it comes to heat, the problem is even more critical. Regular engines, even electric ones, waste energy in the form of heat. In an older Model S, running at 20,000 RPM for 30 minutes, the engine could reach 180 DGC, burning up to 10% of the battery just to keep it running. The Model 2's new motor, with the help of graphene, solves this with 5 times greater thermal conductivity than traditional carbon. The result? Stable temperatures around 110 degrees Celsius, even under heavy load. This represents a thermal efficiency that almost eliminates internal heat losses. Energy efficiency is where it all comes together. With less heat, less friction, and less weight, the Model 2's engine can achieve up to 99.7% battery life, an almost utopian figure for any electrical engineer. For comparison, the Model S's motor reached 90%, and the industry average is between 75% and 85%. This means that almost all the energy stored in the battery is converted into real power at the wheels. It's as if the car stopped consuming energy to keep the engine running and started using everything it has to accelerate, climb hills, or maintain speed effortlessly. And with all this efficiency comes increased durability. When the motor heats up less, it suffers less internal deformation, less wear on parts, and a lower chance of failure over time. Most electric motors fail because excessive heat degrades bearings, demagnetizes magnets, and warps rotors. Here, with the motor operating at lower temperatures and using more resistant materials, these risks virtually disappear. This has a direct impact on service life and maintenance costs, which will be discussed later, but which begins here, with thermal and structural efficiency. It's curious to think that this performance improvement didn't just come from more power, but from a motor that uses less to do more. Instead of relying on larger or more expensive batteries, Tesla optimized the very machine that transforms energy into motion. The new rotor doesn't require heavy liquid cooling or complex systems to prevent overheating. Everything was designed to work with simplicity, and that is rare in an industry where everything seems to be heading towards complications. This ingenious simplicity, combined with extreme efficiency, paves the way for new standards in construction and performance in electric vehicles. With the motor spinning faster, using less energy, and with virtually no thermal loss, the possibilities for the Model 2 expand far beyond an affordable car. It could, in practice, be the first popular electric car with a super sports car engine, but with virtually zero maintenance and a surprisingly low final cost. And most intriguingly, it all starts with a carbon and graphene engineering piece that weighs less than a school backpack. Performance numbers always attract attention, but what's truly shocking here is when these numbers appear in a car that costs a fraction of the price of traditional sports cars. The Model 2, with its new graphene-wrapped carbon engine, achieves 268 horsepower and 350 meters of torque. This is enough to push the car from 0 to 100 km/h in less than 3.5 seconds, which already puts a lot of luxury cars in your pocket. But what's even more intriguing is how it does this with a compact, lightweight, and inexpensive engine that consumes less energy than a high-performance toaster at cruising speed. It sounds absurd, but it's true. This brutal acceleration isn't just a matter of brute force, but of refined engineering. The synergy between the engine's reduced weight, low internal friction, and direct drivetrain allows the Model 2 to deliver nearly instantaneous torque, without the delay typical of many cheaper electric vehicles. This makes all the difference when overtaking, leaving traffic lights quickly, and especially when driving safely on wet roads or uphill. The car responds quickly and precisely, and this completely changes the driving experience. It feels like the car knows what the driver wants to do before they even press the accelerator. Now, a point that surprises even more than the acceleration is the autonomy. Combined with aluminum battery pack, this engine is capable of guaranteeing a practical autonomy of 370 to 380 miles, even in real-world use, with traffic, hills, air conditioning, and everything else. This is rare in the world of EVs, where claimed range rarely matches reality. Here, the engine's energy efficiency means that virtually all of the battery's charge is used to power the car, not to heat or cool the engine. In technical terms, the average consumption of the Model 2 with this set is only 11 kilowatts to maintain 110 km/h, which represents absurd efficiency compared to industry standards. Most EVs with traditional engines require 14 to 17 kWh for the same speed. This difference of just a few kW per hour translates into dozens of extra kilometers at the end of each charge. And more than that, it means fewer charging cycles, less battery wear, and, of course, fewer stops along the way. The engine's lightness also contributes to drivability and comfort. With less mass on the front axle, the car becomes more agile in corners and more stable at high speeds. This doesn't compromise safety, as torque is delivered progressively, and stability is monitored in real time by Tesla's systems. It's the same sensation as driving a sports car that doesn't require Formula One driver skill. Everything responds naturally, smoothly, and precisely, even with all that power hidden under the hood. Another highlight is its handling on hills or with a full load. Many cheaper EVs struggle when they have to pull the car uphill with 4 people and luggage. The engine simply overheats or loses efficiency. In the Model 2's case, high torque and ability to maintain a low temperature, even under extreme load, ensure consistent performance. Whether climbing a mountain or navigating heavy city traffic, the engine maintains its power delivery smoothly, without straining the electrical system. The combination of torque, range, and efficiency creates a package that's hard to beat. No other car in the same segment, with this price and proposition, delivers as much. And this completely changes the way consumers view electric cars. Until now, it was common to think that affordable EVs had to sacrifice driving thrills, range, or robustness. The Model 2 defies this logic by delivering all of these features, complete with acceleration that would scare even supercar owners. And all this performance comes without the need for sports packages, expensive upgrades, or special editions. It's all integrated into the car's base design, demonstrating that this isn't a marketing ploy, but rather engineering applied with intelligence. If there's one symbol that electric vehicles have truly entered a new era, it's this lightweight, responsive, and truly autonomous engine, which proves that performance and affordability finally go hand in hand. For decades, the automotive industry has relied on a handful of extremely expensive and scarce elements to manufacture efficient engines, the famous rare earth metals. Names like neodymium, terbium, and dysprosium, which rarely make headlines, have always been behind the most powerful electric motors. But all that is changing. The Model 2's new engine completely dispenses with these substances, and this changes not only the car's economics, but the entire global production chain. Tesla has achieved a rare feat, creating an engine without any rare metals, and yet more efficient than its competitors who remain stuck in the past. This was possible thanks to the use of ferrite magnets, made from simple materials like iron and clay. Although historically considered less efficient, Tesla engineers managed to dramatically improve their performance by applying selective magnetization and thermal control techniques with graphene. The result was a magnetic assembly that costs 20 to 50 times less than a neodymium equivalent, without losing efficiency. This change alone represents a significant savings per unit produced and paves the way for other manufacturers to follow suit, if they have the technological capacity to do so. Just to put it in numbers, while a traditional PMSM motor costs $2,500 to $3,000, the new Model 2 engine could be produced by less than $1,000. And it's not just because of the magnets. Tesla also started Taos recycled carbon fiber, reused from old cars or discarded parts, instead of virgin fiber, which is expensive and in high demand in the aerospace industry. This has reduced the cost of the carcass by up to 40%, without compromising strength, lightness, or performance. Circularity entered the equation, and this can become a marketing asset as powerful as the performance itself. This more sustainable approach also drastically reduces the vulnerability of production to international crises. About 90% of rare earth metals come from China, which poses a huge risk in the event of political changes, embargoes, or trade disputes. By completely cutting this dependence, Tesla ensures industrial independence and much safer price stability in the long term. This not only protects the company but also directly benefits the consumer, who doesn't run the risk of seeing car prices rise overnight because of a diplomatic dispute. Another factor worth highlighting is the environmental impact. Rare earth extraction involves extremely polluting processes that leave toxic residues and cause lasting damage to soil and groundwater. By eliminating the need for these materials, Tesla significantly reduces the ecological footprint of the Model 2's manufacturing, making it truly more sustainable, not only in its use, but also in its origins. This gives new meaning to the term clean car, which is often used superficially in the electric car market. It's worth remembering that other automakers are stuck with production structures that weren't designed for this new scenario. Giants like Ford, GM, Volkswagen, and Toyota still rely heavily on external suppliers, imported parts, and inflexible assembly lines. Tesla, on the other hand, follows the philosophy of full vertical integration, where every component, from the engine to the software, is developed in-house. This allows the company to implement these innovations quickly, without having to wait years for suppliers to adapt